this was enough, and they followed up, of course, with more observations, to tell us that there was a new family of particles, as it happened, made by a new set of quarks, fundamental constituents that no one had ever seen before. Now, in the way that things go, this discovery, done with great labor in 1977, is now how our colleagues calibrate their apparatus when they turn on. So Fermilab is a big participant in the GMS experiment in CERN, the Large Hadron Collider. They turn on, they run 15 bits of guidance data for a lot of events. They draw very clearly the three peaks of the Upsilon family of particles, but you see now not with particles, a few events, but with tens of thousands in the peaks. So this is a progression from discovery to calibration. There's a third step that people worry about in which a new discovery becomes first a calibration and then a background for future discoveries. It hasn't happened very much for Upsilon, but it has happened for other things that we found here at Fermilab. Okay. So let me say just a word about why this matters. Well, first, it's nice to discover a new family of particles. By comparing the spectrum of these states, which was then elaborated by other experiments, with the spectrum of states discovered only a few years before made of charm quarks, we could learn that the force between quarks is independent of the name of the quarks. That's very important. It speaks to our theory of the strong interactions. The quark itself turns out to have a long lifetime on the particle scale, about 1/trillionth of a second. And it has been a vehicle for studying the structure of the weak interactions and learning how they're put together and works, and has given rise to at least 3 accelerators being built, electron-positron accelerators. Actually, a 4th is about to come into operation now. Rewarded some theorists with a Nobel Prize for having made some conjectures about the weak interactions, and it's just given rise to a whole industry of further inquiry. Okay, so that's the discovery of the Upsilon or the B quark. Another thing that we started doing around the same time was to do new kinds of educational enterprises. Very early in the 1980s, we started a program of Saturday morning physics in which high school students would come here for 10 Saturday mornings in a row, get lectures and tours and occasional hands-on treatments. So here's one of the early classes. Another thing that happened is that some of these kids are too young to drive, and so their teachers would drive them and stay here for the lectures. So give up 10 Saturday mornings in a row for the whole morning. And we met some quite exceptional teachers in that way and discovered that we could learn quite a lot from them. Many of them have become certified master teachers and leaders of the physics teaching movement after that. So that was very instructive for us. We began a program with Fermilab Friends of Science Education, the education office, of bringing children here for prairie tours, in which they could do hands-on things, learn from the prairie. So here are school students doing that. In time, we were able to build the Science Education Center, subsequently named for Leon Lederman. So here's a middle school group coming to tour the Science Education Center with their classes. Many of you may have been there on weekends. Our colleague Jerry Zimmerman, who's named Mr. Freeze, although I like to call him Dr. Freeze or Professor Freeze, has entertained and enlightened lots of people of all ages with his demonstrations of liquid nitrogen and the wonders of that. There he is, covering himself with snow. And if I could get 10% of that delight from you tonight, that would be really nice. Here are kids and teachers at the Science Education Center. Fermilab people, Leon Lederman, Marty Bardeen, a few others, plus many people from the community who are looking for a way to improve science education, helped establish the Illinois Math Science Academy with state funding, a residential academy, which has at least one distinguished graduate that we've seen. Here are some kids in their new laboratories. And part of the program of IMSA is the students go off on Wednesdays to do internships. And here's a group of IMSA interns and their Fermilab mentors in the atrium. don't neglect graduate education. Graduate students at Fermilab, so they're at other universities, but they come here to do their work, have so far deposited 2,188 PhD theses. On an earlier occasion, we actually arrayed all of them here in front of the stage. Now so many of them are coming in electronic form that it's not so impressive to show the file names. But that's a lot of PhDs that we've helped make, and a PhD is for society for 50 years. So these people are valuable to us, whatever they choose to do. Okay, I want to say some words now about the Tevatron, which was our second great accelerator. It was a dream of Wilson early on that it might be possible to go beyond the original energies. The specifications for the Fermilab machine were to reach 200 billion electron volts, which, as we saw, happened in 1972. He wanted to deliver more, and eventually delivered stable running at 400 billion electron volts. That enabled, by the way, the discovery of the Upsilon particle and the B quark by the Letterman group. At the original design energy, that would not have been possible. So the higher energy benefited from that. Eventually it was possible in short bursts to go up to 500 billion electron volts, but Wilson wanted to push for higher. To do so required changing technology in two ways. One was to replace the old-fashioned electromagnets in the main ring with superconducting magnets that can give you much higher magnetic fields and therefore bend in a circle particles at much higher energy. And also, because they don't heat up, don't waste electrical power by heating up the copper in the normal magnets. So if you can only make these work, it is a great benefit to building an accelerator. Well, through a lot of hard work by people here at Fermilab and elsewhere, and this goes from the people who invented the superconducting substances, niobium titanium in this case, the ones who made the strands, the cables, my colleagues here, who discovered how to make a magnet that would withstand the pressures that happen when you excite it to very, very high magnetic fields, learned how to build this machine. And it was a real tour de force on many, many accounts, allowed us to double the energy of the original machine in the same ring. Originally, we reduced the power consumption by about a factor of 3 while doubling the energy, so that was a fantastic step. Here at the top, you see the magnets of the original main ring. On the bottom, you see the magnets of the Tevatron, the superconducting machine. Wilson claimed that he had always intended to build another machine there, and that's why he left the holes in the magnet stands. He might have done it to save material and cost as well, but it was an inspired choice, however it happened. If you're going to build a superconducting machine, you have to keep the superconducting material at very low temperatures, in our case about 4 degrees above absolute zero, and if you're going to do that, you need a very big refrigerator. So we had, for a time, the largest helium refrigerator in the universe, run by this set of people. It's out there across from the CDS building, now called IARC. So here is the great moment at which the new Tevatron operated and reached the highest energy anybody had attained at that point, 512 million electron volts. A lot of happiness there, a lot of relief probably as well. More celebrations. So, Letterman pouring some substance. Wilson was back for the occasion and was suitably pleased. 4 of my colleagues who were particular heroes of this effort, Alan Tolstrup on the right, who was a big driver behind making the magnets, understanding how to make the magnets, Helen Edwards, who was designed and implemented the machine with a big team of people, Rich Orr and Dick Lundy, who were in charge of manufacturing the magnets and other things. They're on the occasion here, they're dressed not for work, but because they were at the White House to receive the National Medal of Technology for their fantastic achievements. Okay, so we're accelerator builders at this laboratory. It is the National Accelerator Laboratory. And accelerators can be used not only to go to the highest energies and to do particle physics research, but for medical applications. And for a number of years, the beam for the LINAC was used when it wasn't required for other purposes to make a beam of neutrons that could be used for cancer therapy for soft tissue cancers. So on the right, looking at CAT scans, one of my colleagues who was a leader in this enterprise. On the left, showing off his six-pack abs, or abs of steel, one of our radiation technicians, showing how a patient would be arrayed there. So there are a lot of people treated for soft tissue tumors using these techniques. Protons are another way of treating certain cancers. And my colleagues here built a compact proton synchrotron for the Loma Linda Hospital in Southern California, which has now treated many people for things like prostate cancer and other things, and which has given rise to a spread of proton therapy for certain kinds of cancer, including a number of centers in this area modeled on the device that they built. Okay, so what's the Tevatron used for in particle physics? There are two ways of thinking about it. One is to use the beams of higher energy to use extracted beams and to study what happens. I want to give you two examples, both because they took a long time to perfect. It's maybe in the old days, maybe in a high school physics lab, you go into the lab and you get an idea, or you're given an idea and you do the experiment and it works or doesn't. Often, what we call experiments are institutions that live for a decade or a decade and a half or 2 decades, in which people come together pursuing some initial goals. They learn better and better how to accomplish those. They get new ideas along the way. So this is an experiment to look for the properties of what are called charmed particles, those made of the fourth quark and light quarks. And this was the second major experiment in that sequence. The first experiment had a number of near-death experiences, although it had a number of very good ideas in it and produced some intriguing initial results. But there were two important innovations here. One was to take advantage of a technology then being developed around the world, but really put into excellent application here, of what are called silicon microvertex detectors. These are detectors that allow you to localize the position of charged particles to a degree that was previously not possible in an electronic detector. And so that was a great advantage. These are particles that decay weakly after a lifetime that's around a picosecond, around a trillionth of a second. And so that means that even at high energies, they travel maybe a millimeter or a little bit more before falling apart. So you've got to be able to look very closely. And if you want to gather large samples of them, you have to do it with an electronic detector such as this. So here's a picture of the front end of that detector. The beam comes in. There are little targets there. The targets are interleaved with the silicon microvertex detectors. And this was the first time that such techniques really led to first-rate physics results. Now, there was another challenge here, and that is that if you're taking lots of data and you have to filter out the wheat from the chaff, you have to be able to do computer processing in a way that is fast and cost-effective. Fermilab was always demanding for computing. Here are the first disk drives at Fermilab. So they're about 1 meter in diameter. I think they weighed about 1.5 tons. They spun around very fast. And the total capacity of that is that it would just hold the PDF file of my talk. But we were at the frontier. We did have online computers, PDP-11s, for data acquisition. And we did have a monster computer, a CDC 6600, which was built of basically military-grade steel. I think it could have sustained a direct hit from a howitzer and still operated. Magnetic tapes. I brought, just for your amusement, since I'm a man of a certain age, this was one of the first computer programs I wrote here at Fermilab. Which led to the discovery of the W boson, by the way. now, well, okay. So they made all this work, and what enabled the computing was that, again, these were currents that were in the air. It was very expensive to buy computers. Mainframe computers were big, and they were not so fast, and so on. So one of my colleagues here, Tom Nash, realized that microprocessors were becoming fast enough, capable enough, you could put enough memory with them. And he and his team started building supercomputers out of little boards of microprocessors. Other people were trying similar approaches around the country and around the world. And over time, this evolved into buying boards, buying computers. We now have the huge farms of computers here at CERN, in the cloud. You know, Amazon and Microsoft and Google are in this business big time. This is one of the places that the idea started, and that people, by the need to analyze their data, made it work for the first time. These people also, and you'll see some of them here, together with some of my theory colleagues, built a special purpose machine for a style of theoretical computing called lattice gauge theories. It's a method of solving the theory of the strong interactions, and this has, again, led to great improvements in our ability to understand that theory and to calculate the properties of the proton and neutron and other particles. So, great achievement. So that was the first experiment I wanted to tell you about. The second is an experiment called KTEV. This is something very subtle. There are particles called kaons, hence the name of the experiment, kaons plus tevatron. And they display a slight difference in the behavior of matter and antimatter, which is very puzzling for a long time, and we didn't have all the information we needed about that. So the experiments here, again, this is one of a line of experiments. This is the culmination of a line of experiments. Similar experiments at CERN, a nice rivalry between the two groups, trying complementary techniques. Here's one of their pieces of apparatus, a beautiful crystal calorimeter made of cesium iodide crystals. It's out in the experimental areas. Here's their control room, a bunch of them there, and a guy dressed in his underwear in the back. So they succeeded over time in comparing the behavior of matter and antimatter and finding a difference of a new kind and giving us a new insight into the way this so-called CP violation, charge parity symmetry violation, happens. And together with their friendly rivals at CERN, were able to give us a new information about that all goes into our understanding of the weak interactions as we have them today. Okay, so another interlude about Fermilab and its natural areas. One of the ideas from early days to make this a really quintessentially American laboratory was to restore the land to the condition it was in before, and that meant restoring a native prairie. So we've had people gathering seeds from the prairie plants, sorting the seeds, planting the seeds, and of course having prairie fires. The point of the prairie fires is that the native grasses have deep roots and the invasive European species have shallow roots. So if you have a prairie fire every year, under controlled conditions of course, you can weed out, selectively weed out the invasive species and be left with a native prairie. And so there's a huge area of the inside the ring, as well as some other areas on the west end of the laboratory that have been restored to native prairie. And it is quite wonderful to see when the plants reach this high toward the end of the season. We also have, in addition to the Prairie Project, an organization now called the Fermilab Natural Areas. It's an organization of the community and Fermilab people, which takes great pleasure in the natural features of the laboratory, as well as taking care of it. Okay, the second piece of the tevatron was to go to much higher effective energies, not by hitting protons on a target that's fixed, but by hitting a proton beam together with an anti-proton beam. Now this is a good trick. Protons come out of a bottle of hydrogen. Antiprotons don't come out of a bottle of antihydrogen, so you have to go to great lengths to make them and to trap them and to gather them into rather dense beams. This was done in a facility out to the back called the antiproton source, the antiproton source, in which there's something called the debuncher and the accumulator, two aspects of it. So we had here at Fermilab the largest concentrations of antiprotons anywhere in the world for quite a long time, and used them in two ways. One was to just take the antiprotons and collide them with a target, which might be a gas jet or something, tune the energy to make particles we wanted to. And this wonderful device that I have here is an element of a detector used for that purpose. So this is a piece of lead glass, which has wonderful properties for responding to electromagnetic radiation. My ultraviolet pointer shows you internal reflections so that it gathers all the light back to a place that you can detect it with a photomultiplier tube. It's the same material that's in your grandmother's fancy crystal, used here for detectors, and it's one of the very beautiful objects that my colleagues make. This was a spherical detector in which that's one of the elements. So that's the fixed target purpose. The real goal was, however, to make protons and antiprotons go in opposite directions around the main ring. And to do that, we had to give them directions. So the protons go this way, the antiprotons go this way. As you drove into the main ring road from just behind us, you would encounter this sign, and if you were a jogger or a blader and we wanted to be protons, you could go to the left, and an antiproton, you could go to the right. Anyway, that is the way that they circulated. And it was fantastic technology that my accelerator colleagues developed, first to do this at all, and then to do it in such a way that they would make the beams of protons and antiprotons spiral around each other so that they only collided at the detectors where we wanted them to, and not just waste themselves on each other. There were two big collaborations. These were big collaborations in those days, 300, 400, eventually 600 or 700 people, the CDF detector. This is another illustration of the importance of international participation at Fermilab. We would not have started this detector as quickly as we did without the intense participation of Italians and Japanese physicists. They were really essential to getting us started. Others joined us as we went on. And here is the so-called D0 collaboration. Again, this is around the time of the great collective discovery of these people, with a bunch of their flags shown here as well. In this very auditorium, in early 1995, there were seminars by the CDF and D0 collaborations in which they announced the discovery of the top quark. This is yet another fundamental constituent of matter. It's something that is much heavier than all the other particles. It weighs as much as an atom of, we used to say gold, but it's really osmium. Anyway, very heavy. But unlike an atom, it's not made up of lots of protons and neutrons. It's just a beam. As far as we know, has no internal structure. So it was required to do this. It took 10 years of serious effort at the Tevatron in order to make this happen, and it did happen. Here are a couple of examples, slightly enhanced. One event from D0. If you know how to look at this, you'll see that the two towers on the left make a W boson. A little stub up at the top makes a B quark. This line, the blue line, is a muon. That line is a neutrino that is represented by missing energy. That's another W boson, and this stuff down here is another B quark. And that was the signature of a top quark and any top quark being produced. So just a beautiful event in which you could see everything. CDF had their own microvertex detector from early days, flowing up the vertex there. You can see detached vertices representing two B quarks there, and the other characteristics of this event mark it as a good candidate for a top quark. So that was a big achievement, noticed by the worldwide press. In different languages, particle physics is over because it's got this last secret, or something like that.